Yeah, so thanks a lot, Michal, and thank you all for coming to this. So I heard it's a bit of a mixed audience, so I'm going to try to be a bit more introductory, and so but also that means that you can stop me at any time for questions and whatever. And also, I don't know if any of you, probably not so many, were in the workshop this week. Apologies for that, because it's going to be an extremely similar talk than the one I gave on Monday. But anyway, hopefully it's interesting. Yeah, so as Michal is saying, this is going to be related to open quantum systems, but more specifically to open quantum systems in relation to quantum algorithms and quantum computation, because there's been some nice recent developments on how to model certain kinds of, let's say, open dynamics of many-body systems, and I'm going to show you a small part of that progress that is happening nowadays. And so what I'm going to show is work, in particular 3 papers that are two of them are on arXiv already with my collaborators Cambyse and Daniel. And the other one, which is going to appear hopefully next week, at least this is what I told Mateo. And Mateo is my postdoc in Madrid. And yeah, we'll talk about the different results as we go. Okay, so I want to start with a kind of the big question that I think hopefully many of you kind of sympathize with or at least care about to some extent, no? Which is, there's all this fuss about quantum computers, right? And one can ask, why do we want these quantum computers in the first place? No? And for me, a nice particular case of this question is this, no? Is whether quantum computers can help us understand quantum physics in as much detail as possible, and in particular, a part of quantum physics that is particularly mysterious and particularly difficult, I guess, no? Which is quantum many-body systems, right? So we know that when you put many quantum systems together and they interact strongly, right? Describing them, is very difficult with usual ways or by brute force methods. So hopefully, quantum computers, can allow us to push the barriers of physics of quantum physics as we understand them, right? And to this question, I believe there's a very clear answer that hopefully you agree with, which is that the answer is yes. Otherwise, I wouldn't be here telling you this. And the reason why you can say this is because we have some idea of how to program and probe, interesting things in quantum physics in computationally efficient ways. No? And here, computationally efficient means within the paradigm of quantum computers, right? So we have some understanding of how quantum computers can allow us to efficiently explore complex quantum physics, right? So this sort of leads to a bit of a research program. I want to maybe outline it now. What is this research program, and what is an example of this? So in the program, we want to identify families of physically interesting processes, right? There's a very nice example, which is the most common you've probably heard of, which is unitary dynamics, no? In unitary dynamics of many-body systems. So just the natural reversible dynamics as described by the Schrödinger equation, right? Essentially, you take a state and you apply a unitary matrix to it. The way to model this, of course, is that the unitary is generated by some Hamiltonian, and typically in the many-body context, this Hamiltonian is a sum of local terms. Okay, so nothing too complicated for now. And this could be, an IC model or many other things, whatever you want. And for this, we have, I think, a good understanding of how do we simulate this in a quantum computer. The reason for that is that we know how to approximate this type of unitary as a quantum circuit. And if you heard, for instance, of Trotter formulas, of Trotter approximations of these things, where you essentially decompose this big matrix into a product of smaller ones that end up being the quantum circuit, this is how you will do it, okay? So we know how to do these things in quantum computers and we've known them for I don't know how long, maybe 30 years or something like this. Not only that, but we also have some understanding of how hard is this problem computationally, right? The reason for this, in this case, is pretty trivial, is because, kind of almost by definition, if you're able to simulate this kind of process in the most general sense for polynomially large times, polynomial in system size, the family of problems that you're solving is BQP hard. So that's kind of as hard as the hardest class of problems that quantum computers can efficiently solve. Right? And this is pretty much by definition, right? Because basically these things are essentially pretty much the same as circuits, right? So what I want to talk about now is essentially a different family of physical processes that is not unitary dynamics. No? In particular, I want to talk about the thermalization of many-body systems. The process that I want to describe is the one in which you start with some arbitrary state, like a 0, and then you always end up in some sort of equilibrium or thermal state, right? And it's a bit funny, but before this, which seems a reasonably simple process, we don't really have such a good understanding of all these columns. Even if here they're trivial, here the picture is a bit more complicated, right? And essentially, what I want to talk about is that we're sort of making good progress along all these lines. And the results I will show are exactly about these 3 lines that I'm mentioning. Okay, so what more specifically, what do I want to talk about? I want to talk about Gibbs states, okay? So basically, this type of quantum state, exponential of a minus beta h, where h is some Hamiltonian. This is, of course, a very common state in physics, right? I mean, everything is essentially in a temperature with a larger environment, right? So it appears basically everywhere, no? And when you study statistical physics, this is pretty much the only thing you study. Not only that, but also these states actually also are important for computational reasons. For instance, there's a lot of like Monte Carlo algorithms and things like this, both classical and quantum, or optimization problems, also machine learning, and so on, where being able to sample from these distributions is interesting for computational reasons, right? And there are also some nice connections between, let's say, computational physics, which I will talk a bit about, but they've been also understood in the context of classical physics also. So the point here is that I want to kind of put forward, which is it's a bit peculiar, I think, and it's a bit of a peculiar situation, is that okay, we have this thing, and we know what it is, and Gibbs wrote this like 150 years ago, or whatever, no? And this is the most common state in physics, no? The thermalization process is very common in physics. It's so common that one will expect that it's actually very easy to simulate on a quantum computer, right? Just because nature does it all the time, so we should also be able to do it with not so much effort, right? And actually, this is maybe seems like it should be the case, but it's not necessarily the case actually. And this is the kind of thing where we've been making progress actually. But to show you why this is a bit problematic, I want to talk a bit more about what is this process of thermalization, right? How do quantum systems thermalize? The simplest example you can typically think of is where you have a qubit, for instance, a single qubit, that is interacting with an environment that you somehow assume is already thermal, and the qubit is not. And the qubit is going to interact with the environment, and it's going to equilibrate to the temperature of the environment, right? So this is what this is doing. And of course, the way you typically model it is through a Lindbladian, so a Markovian master equation that, if you wait for long enough, it takes you to always the same state, the state at the temperature of the environment. Okay. So what is this Lindbladian? What is this master equation? Oh, this is sometimes working, sometimes not. This one.
The pointer in this clicker.
Is there also a pointer here?
No, it's an electronic pointer.
Oh, so oh wow, okay. Nice. This is too modern for me. Yeah, thanks. Yeah. So what is this Lindbladian? How do we typically model thermalization? So for this, I want to start introducing some notation. Okay. So we have the Hamiltonian of the system that we want to study, and this Hamiltonian has an eigenbasis. Okay, things are going to be written in terms of this eigenbasis, and then we have an interaction with the bath that is modeled through some interaction Hamiltonian, right? Where you have some observables that act on the system and others that act on the bath, and you have a coupling constant as well. Okay, through these two things, the Hamiltonian of the system, and the interaction one, you can define this thing, the jump operators. This is essentially the following: you take the observable A that acts on the system, and then you write it essentially in the energy eigenbasis, right? You sandwich with a couple of eigenstates that are far apart by a fixed frequency. Okay. Yeah. So this is defined in terms of the observable and the eigenstates of the Hamiltonian. Okay. Once you've defined these jump operators, you can define the master equation. And this is a very old result, and I think at least the first rigorous derivation of this appeared in the papers by Davis in the 70s. Is the master equation that takes you to the Gibbs state, no? And this is the following, right? So you have these jump operators. This is the typical, Lindblad form of a master equation, and it is defined through the jump operators, and also this function here, which has to do with the correlation function of your bath. So the information about the temperature is here, actually, no? And this somehow guarantees this and this together guarantees that you're going to be driven to the steady state, which is the Gibbs distribution. Okay.
What do we need to assume about interaction?
This is my next slide, actually. Yeah. I'm going to go to that, yes, in a second. But first, let me say a couple of things about these Davis maps, okay? The first thing is that, for sure, under some, they always have the Gibbs state as a fixed point. It could have more fixed points, but under some conditions that are not so hard to satisfy, the Gibbs state is going to be the unique fixed point, okay? So for any initial state, you typically go in, again, under some conditions that are not general, but they're not terribly hard to satisfy, you always go to the Gibbs state, okay? But there's actually something stronger that holds. And this is something I want to talk a bit about. It's this property of quantum detail balance, okay? And the definition of this property is essentially this, which maybe seems a bit obscure, but what this is a property of the generator and the fixed point, okay? So you have the generator and you have the fixed point here. It's basically this identity. And really, maybe the best way to see this is that you're able to define some sort of scalar product, which is this KMS scalar product here. And what this is saying is that the generator is Hermitian with respect to this scalar product, more or less. The nice thing about this is that it directly implies that the give state is a fixed point. Okay. I mean, this is not super hard to see. Basically, if you put sigma here, then you get the identity here, and the identity into L dagger is 0. So, yeah. So this implies this. Okay. So this is the kind of the property that we want for my master equations in order for them to have the right steady state. Right? And to answer that question, this master equation that I was writing earlier holds in a particular limit, which I'm going to call here. I mean, it's essentially a weak coupling limit, but here in this talk, I'm going to call it the ultra weak coupling limit. So for this to hold, what you need is that the coupling constant between your system and bath, so this coupling constant, is very small. In particular, is much smaller than the smallest frequency of your system, right? So in the Hamiltonian here, I can define a bunch of frequencies. For the qubit, it will be just the single level spacing between the two levels, no? So the coupling constant has to be much smaller than all of these numbers, no? So essentially, what this means is that my system is rotating under its unitary dynamics, and the effect of the coupling has to be much slower than the effect of interaction of the system of the Hamiltonian of the system, right? So this is what weak means, no? And essentially, what this means is that you can take the rotating wave approximation. For those of you who know that what that is.
Is it the same as so-called quantum limit of the coherence?
I don't know what that is. I'm not sure. I mean, I guess if with the coherence,
that we are somehow selecting the energy eigenbasis as the preferred basis.
Yes. It implies this. Yeah, because then what this is saying is that in the master equation, you're somehow diagonal in this jump operator. So you have the same frequency here and here. So the steady state is going to be diagonal in the energy eigenbasis. Yes. And actually, that's important because this equation has this, but the next one I'm going to show doesn't. Sorry, next. Yeah. So okay. So the problem we have now actually is that let us consider many body systems, so Hamiltonians of many interacting particles. Okay. So now I have a local Hamiltonian, and I can write it in the energy eigenbasis. And what's special about this Hamiltonian is that since they live in a Hilbert space that is very big, in particular exponentially large in the number of particles, the number of energy levels is also exponentially large in the number of particles. Okay. But this is so, but still the Hamiltonian is local. So actually the possible range of energies, so the range in which these eigenvalues can live, is only polynomial in system size, right? It can go from some E0, which will be the ground state, to some E max, which is the largest possible energy, which is at most proportional to the number of particles, right? So if this is so, the spectrum of this basically, what I'm doing with the spectrum here is that I'm trying to fit an exponential number of eigenvalues into a polynomially large range. Essentially, what this means is that for sure, and it could be, there's going to be also degeneracies and so on, but for sure, at least, the smallest frequency is going to be proportional. Well, it's going to be exponentially small in the system size. Okay, I'm basically bounded to having this, and typically this is going to be the case in many body systems. Okay, so the level spacing, the typical level spacing in many body systems is exponentially small in system size.
Sorry about this Davis dynamics. Like, does it work if you have degeneracy, or?
Yeah, you can make it. Yeah, you can make it work. Then the jump operators can take that into account. Yes, so
then technically you can have massive degeneracies, and it would.
Yeah, you could.
Fit exponentially.
Yeah, you could have that, but that's not what happens in many body systems typically, because you have like level repulsion and things like this. So yeah, so that's a situation that could happen. Yes, and it's more or less what happens actually when your many body Hamiltonian is commuting, for instance. But okay. Anyway, so now if we accept this, which okay, maybe it doesn't happen all the time, but it's going to happen most of the time that this is the case, we can go back to this assumption of the ultra-weak coupling and look at what this means, no? Because this number now is exponentially small in system size, and this is the coupling constant. So what we're saying is that for this Davis map to be valid, for this master equation to be valid, I need the coupling with the bath to be exponentially small in system size. And this is very problematic, right? Because what is, how does my coupling with the bath know how large my system is? No, and in particular, exponentially small is really, really small, right? So what does this mean exactly? And another way to see why this is a difficulty is looking at the jump operators, right? Because if we accept that these are somehow the operators that the bath applies into the system through their interaction, and they are these operators, essentially generating these operators requires a super large energy precision, no? a very good energy precision. For instance, you can write them also as a Fourier transform, and the Fourier transform goes from -infinity to infinity. No? So you will require in order to generate this these operators, you require extremely long times. No, I mean, of course, you could cut this integral, but you're going to have to cut it at very long times. No, exponentially large in system size, typically. So it's not clear. I mean, it's very strange to think that in many-body systems, this is what nature is doing when you want to thermalize these many-body systems. No, so it seems that basically the point that I want to make here is that this Davis map, which is the typical model of thermalization that you see in textbooks and so on, doesn't really seem to apply when the system is, reasonably large. And of course, in many settings, like in quantum optics and so on, where you have, just a few qubits or a single qubit interacting with some bosons or whatever, then this assumption is fine. But in many-body systems, it seems that this model really is not giving us what we want, actually. Not only that, but also the jump operators. Even if your Hamiltonian is local, your jump operators are extremely non-local. No? So somehow you have a path that is interacting with the system in a very non-local way, which seems very, very unnatural. So this is the problem that we have, actually. Way we model.
Saying that this will lead to thermalization, but in real life, thermalization will happen much earlier because of other things.
I'm saying,
or that the whole model is wrong. I'm
saying this is not a good model for many-body systems. I mean, it will be a good model under this assumption, but in order to see this, you need a coupling that is super small. So you're never going to see this kind of thermalization, basically, as a natural process, right? Okay. And this is so now I want to turn a bit the page into the algorithmic side of the story, because this problem that I'm talking about is not only just a problem for the way we model thermalization, but it's also a problem for the way we model thermalization on a quantum computer. Okay, and for this, maybe I want to mention how do we model thermalization in classical algorithms, and also for classical systems. There's a very standard way, which is this one of these Monte Carlo algorithms, like the metropolis sampling. And essentially, what you do there to generate samples of a Gibbs distribution is, you have some updates. So you generate some string of zeros and ones, for instance, and you keep updating it in a way that somehow respects this detailed balance property. So this detailed balance property has an analog in the classical setting, which is essentially satisfied by this conditional probability. And what this means is that I have an algorithm that you take as an input some string, then it updates, and then you take it or not with a thermal ratio, basically. And this algorithm requires, that you have this detailed balance, and also that you're able to do updates that generate these thermal samples. Okay. And you need that these updates are local, and in the classical case, this is easy because the eigenstates are product states, right? They're just, for instance, for a classical Ising model, they're just ones and zeros. And also, you need to be able to implement efficiently these updates. The thing is, because of this, if you think of these operators as the analog of the updates of the metropolis algorithm, then in the quantum case, these are neither local nor efficiently implementable. So we have a problem when we want to generalize metropolis sampling to the quantum case. And there were proposals about how to do this quantum metropolis sampling, and in particular, there's this quite famous paper from a few years ago that, for instance, requires some sort of phase estimation algorithm that I'm not sure it's. It requires some precision that I think is pretty much unrealistic, actually. So it's not clear that this works very well, and this is something that you should be able to do in practice. And actually, beyond this algorithm, there's actually many algorithms for preparing Gibbs states in quantum computers that people have devised. And I'm citing a bunch of papers here. This is probably old already. That fall into different families. There's some variational ones. If you're aware of variational algorithms, there's some that mimic dissipation, but in a way that maybe was not completely satisfactory, and also preparing some purification. So this is a whole family of things, but. Many of them didn't really have good guarantees of how well they converge, and they didn't really seem to capture the real process of thermalization, right? So there was somehow something missing here in the way we thought and devised these algorithms, basically. But luckily, there's been some nice recent progress about this, and I want to here highlight the paper that I think triggered a lot of the efforts that I'm talking about now, which is this paper by, I guess, people who were in Caltech at some point and are no longer there. And here, essentially, what they do is they construct another Lindbladian, which is different to the Davis Lindbladian. But this Lindbladian has some nice properties. And really, here they didn't do it from the open systems point of view, but really from the quantum algorithms point of view. This Lindbladian has nice properties. In particular, the jump operators are now quasi-local. What this means also is that they're also designed in such a way that they're implementable on a quantum computer. So you have the two requirements that the classical metropolis sampling had. And not only that, but these two things, they can be made compatible, and this is kind of the non-trivial thing that they show with exact detailed balance, with the property that I showed a few slides earlier. And actually, until not so long ago, I guess until this paper came out, it was not clear that these three properties, that you could satisfy them at the same time. Actually, none of these previous quantum algorithms have these properties at the same time. Actually, And the way I do it is actually, I mean, how do I say this? I mean, it's not simple, but it's, you know, it's the thing you would think about maybe. No? So you have the jump operators that you define in a different way, and now what you do is you define a function that is like a filter function. Okay, this filter function you can take it to be a Gaussian. I mean, it can be a bit more general, but just think of it as a Gaussian with a width, right? And the thing is, you can choose these functions and other things in the algorithm, you know, in such a way that you define these jump operators, where now since you have a filter, this function decays at long times, no, times controlled by this sigma e. So this is an operator that doesn't really take infinite time to be generated. It takes as long as this function takes to decay, basically. No? So it's also local because of Lee Robinson bounds, if you know what this is. No? Because basically, this is an integral from minus infinity to infinity, but this function becomes 0 at long times. So really, this object remains localized around some vicinity of A. Okay, it doesn't have to be across the whole system, and it's not a very complicated object. So because this f of t really is the only difference between this and the equation from a few slides ago. No, of this. I've just introduced this filter function, okay? That's the only difference. And the nice thing is that you can still do this while keeping this exact detail balance. This is the very non-trivial thing that this does. So now you might think that this is actually, this in this paper is only drafted as a quantum algorithm, actually. No? But one might think that it actually also resolves the problem of, that the Davis equation had. No? Does this actually describe some natural model of weak coupling interaction between a system and a bath? So this is what we try to do, and this is more or less what we've achieved, and hopefully it will be out soon, in the next week or two. Is that we can actually now that we know that this equation exists, we have a target, so we can tailor our derivation of a master equation towards this target, and this is what we did basically. And now we can derive from first principles, meaning we start from like a system bath interaction that is closed, the system bath is closed, no? And then you do the usual steps. And this gives you a master equation in the weak coupling regime, not the ultra weak coupling, the weak coupling, that has all the properties that we wanted. No? That the jump operators are quasi-local, so no rotating wave approximation like the Davis ones had. We still keep the KMS detail balance, the property that we wanted, and also not just that, but we're able to approach the Davis equation in the right limit. No? So when this holds, our master equation goes to the Davis limit. No? And actually, we can do this with error estimates that are rigorous. And for this, we build on some papers like this one by Mosgunov and Lidar, but we improve some of them. So now what we have essentially is that we have a master equation that resembles the exact evolution up to an error, which goes down with the coupling constant as we wanted. But now you don't have these frequencies. You only have some property of the bath, essentially the decay rate of the bath. In this paper of Mosgunov and Lidar, they did something similar, but they have an exponential of t over t bath, actually. So we improved a bit on that, while also including this KMS detail balance, right? And with this master equation now that we have is I believe, a nice model of thermalization for open many-body systems. And one reason I think is interesting is because if you look at previous literature on open many-body systems, like this review here, you see that most of the models that people looked at were just many-body systems in which you have the internal dynamics, the internal unitary dynamics, and then you put some sort of amplitude damping or depolarizing noise on top of it. So really noise that drives you to a state that is not a collective state, let's say. No? So very local noise. And now we have a noise model that really, I believe, resembles interaction with the bath. That is not just a simple depolarizing channel. No, it's one that can drive you to the actual collective given state. No, so maybe it leads to some other interesting like numerical studies and things like this. No.
Sorry, can you comment, like on high level, how you get this effective filtering? Because if I understand you.
Okay, maybe I'll show you with the next slide actually, because this is the master equation that we have. Okay. And I explained it and then I answered your question. So the master equation is basically the same as the one before, pretty much. In particular, it's a particular example of the one I showed before. No, is this where we have these jump operators now, and the jump operators. Okay, now I've written them in the frequency, not in time. But if you take the Fourier transform in time, you get something very similar to what I showed earlier. No? So now we have this Gaussian here that depends on the coupling constant. So when the coupling constant goes to 0, this goes to infinity. So the Gaussian becomes a delta function, and then we recover this, which is the jump operator of Davis. No? And then this thing here is the correlation function of the bath. For those of you, it's related to the gamma that appears in Davis. So yeah, the key thing here is that now we have this Gaussian that somehow modulates, no? And modulates the width of our jump operators. And yeah, to derive this, we go through this essentially very standard steps, and changing some of them. No? And you need some properties of your bath, for instance, that is initially uncorrelated with your system, that is quadratic also, although this is maybe less necessary, and also that the bath is Markovian in the sense that the information dissipates quickly, which basically means that the correlation functions decay fast. And yeah, in order to do this, there's some proof steps that are, if you ever seen the derivation of these master equations, they're reasonably standard, but you have to make them quantitative, and also you have to change some of them for what we wanted. So there's the Born-Markov approximations, the Redfield approximation, and then you need to do some other steps. You need to massage these things a little bit and change them a little bit in order to obtain this KMS detail balance. And your question was, how do we...
Yeah, how you get this weight effectively? Like, how you get this filtering?
Yeah, so the way you do it is by... let me see. So you can... The thing is, you just kind of put it by hand at some point in your master equation, and then you show that, because things somehow depend on the correlation functions of the bath that decay fast and decay with this scale. So essentially what you need to show is that this filter is such that if you introduce it, because of the, if you introduce it, the error that you make is very small because the correlation function of the bath is already 0. Yeah, so I think as a high-level idea, I think this is more or less it. No, you have to just leverage this thing.
Under those assumptions, can one just understand that you generalize derivation of the Davis equation to the scale, lambdas that are on broader scale?
Yeah. I would say so. Yeah, because there's one approximation that we're not making, no? And there's some steps in the middle. Some steps are. I'm not. They're more technical than I'm saying. In the sense that you have to worry about some small details, but yeah, basically yes, yeah. In particular, if you take this to be infinity, then.
So then on the previous slide, when you had the convergence, the rho t exact was what?
This is just the exact evolution. You get the Schrödinger equation of system and bath, and you trace out the bath.
So without doing any exam?
No, with no approximations. Yeah. So because there's a few approximations, so there's like. There's So to bound this, there's some triangle inequality you have to do, and first you compare the exact with the Born-Markov, then the Born-Markov with another one, with the Redfield, and so you have. But you have to do it in a way that is a bit ordered, no? And for instance, here in this paper, they did most of it, but then we put a bit more in order to get this.
The right-hand side, I would expect to depend on the size of the filter, or this is in the assumption the filter.
No, it does, but then since the filter you can put it by hand, we can optimize over it, and then this is the best scaling that we have. Yeah. So because basically this t is a free parameter but you have to choose it to be like this in order to get the best approximation, and the best approximation ends up being this basically. Yeah.
How to understand that the smaller the time correlation of the bath, the worse the approximation?
Yes. You have to compare it to the. Why is this? Maybe what you need to consider is the time you evolve with versus the time correlation of the bath. How do I understand? Because you will expect that the quicker the bath is, the more Markovian your evolution is, right?
Yeah, the simpler or something.
Yes, but. Okay, I don't know if I have a good answer actually, but I understand why you're asking this.
Or it just means that then you automatically need to make smaller lambda. And
I think it's something like this. Yeah, in the end, these things, you have to be careful with how you define the energy scales and so on here. Because of course this thing is, the way we define this actually, you have to think that this whole thing is dimensionless. So this coupling constant doesn't have energy units. The energy units are somehow in here. So I think, maybe there's some, maybe this is too simple to see what's going on exactly to answer that question. Yeah. But I need to keep this in mind because it's an important point actually. Anyway, so now we're done with these master equations, and this is a model that maybe we have. Maybe now you can analyze, and you could even explore it numerically and things like this. So, okay. So now I move on to let's say the quantum algorithmic side of things. Because what they show in this paper that I was talking about earlier, of the Caltech people, is that this family of Lindbladians that includes that includes as a particular case the one we derived, can be efficiently implemented in a quantum computer. And what this means is that if you want to run it for time t, the resources that you would need are essentially linear in time with some logarithmic overheads times something related to this thing here, to this free parameter here. No? And in our case, for the weak coupling Lindbladian we derived, this thing was related to the coupling constant. So this is the time it will take to simulate your master equation in a quantum computer, more or less. And the algorithm, it looks like this. This is like one single step of the algorithm. It's a bit complicated. It will require a fault-tolerant quantum computer because it involves Fourier transforms and block encodings of jump operators and a few things. But it's not the craziest quantum algorithm. No? I mean, for the express quantum algorithms, which I'm not, it uses more or less standard tools in the field. Another convenient choice of this algorithm, a particular case that is interesting for us, and I will talk about it in a second, is what I'm going to call the algorithmic choice, which is the one where this free parameter, you choose it to be beta, the temperature of your bath, just because it's a convenient choice. And it's also nice because it allows us to get some results about the convergence. Because here, I've only just said so far, how long it takes, so the resources that you need to simulate the master equation for time t. But if your aim is to prepare the give state, which is a computationally relevant task, you don't want to know, just this. You also want to know how long you have to wait or how long you have to simulate your system in order to actually get a give state. So what you need in order to get this is a result of this form. Basically telling you that, how long you have to wait, how does the distance between your evolved state and your give state contract with time, okay? How fast do you converge to the give state? And this is something that we know how to answer for this, for some particular cases of this, okay? And this is the next result that I want to show. What we show with my co-authors, with Camille and Daniel, is that this Lindbladian that I showed earlier has the rapid mixing property, which essentially means this, that the distance in one norm between the evolved state and the give state, the fixed point, and there's some choice of jump operators that you need the full algebra and so on for the give state to be the unique fixed point, but okay, you can just kind of define it like that. This distance contracts as following. It has a polynomial overhead in the system size, so this is the size of the system in which the Hamiltonian lives, but it contracts exponentially with time. And this number is just a constant, so it's like 1/2 or something. So if you wait for long enough, in particular, if you wait for logarithmically long times, this thing is going to overtake this, and then you're going to be close to the give state. No? This is what is called this rapid mixing. In order to prove this, we need two assumptions. The first of them is very weak. Essentially means that the H is a reasonable many-body Hamiltonian. No? Essentially, that is local. In particular, what we need is that it has this Robinson bound that I will talk a bit more about in a second. The other thing that is less weak, and we will kind of maybe like to relax, the other condition that we need is this, that you're in the high temperature regime. Essentially, you have to fix a temperature, some beta star, that is some constant that depends on the parameters of your Hamiltonian, not on the Lindbladian, just the Hamiltonian. And if you're above this temperature, because beta equals 0 is the maximally mixed state, infinite temperature, then you know that this convergence is fast. No? So this, together, this together with the result from the previous slide, that you can simulate this Lindbladian with linear resources in time, basically tells you that you have an efficient quantum algorithm for preparing high temperature give states, which is something that was not known before some of these works, and not just ours but also some others. Okay, so maybe I can give you this is going to be one of the more technical slides. Maybe I can give you an idea of how do we prove this, and why this high temperature is important. So the way to prove it is by looking at our Lindbladian a bit more carefully and essentially seeing that because of the way it's defined with these filter functions, the jump operators are quasi-local, which I've been telling you that this is the case, but now we have to make it a bit more precise. And for this, we use this thing called the Lie-Robinson bounds, which essentially tells you that if you have an observable evolving under a many-body Hamiltonian, the evolution of this observable is constrained within an approximate light cone. And what this means is that your jump operator can be approximated by something that is within a region that is near the observable. No? So you have to think of A as an observable that lives in a specific region, in your lattice, for instance. No? And then the jump operator is somehow just addressing on top of it, no? Addressing with exponentially small tails. Okay, this is what this is. And this just follows from the Lie-Robinson bound, from this locality structure of the Hamiltonian. Okay? And now if you choose your jump operators to be single-site Paulis across the whole system, x, y, and z, what you can observe is that there's a limit of these jump operators and this Lindbladian, which is the limit of beta equals 0. And in this limit, what we obtain is a very simple channel that maybe some of you know, which is the depolarizing channel, which is the channel that just outputs, maximally mixed local states. No? And this channel is very simple, and in particular, we know that it has this rapid mixing property because it just acts on single sites, so it's easy to analyze actually. No? And we know that it converges very fast to the fixed point. So then what we need to do is we need to somehow extrapolate from this point. No? And this is maybe the trickier part, is that we have to consider how this Lindbladian under these conditions is a bit of a perturbation from this depolarizing channel, and we need to use some sort of continuity argument. And for this we use some norm that I didn't know about, but my co-authors did, from this paper on classical mathematical physics in the 90s. They defined this thing called the oscillator norm, and this is somehow the right thing you have to use in order to extrapolate how the rapid mixing at some point relates to the rapid mixing at a point that is a perturbation away from it. No? So how this rapid mixing property is a stable property actually. And then with all these ingredients, you have this result. Okay. Hopefully this at least gives you a high-level idea of how we do this. Okay. So now that we have this result, we can talk a bit about how this, what this means for a problem that is, I believe, interesting from the computational and complexity theory point of view, which is really preparing quantum Gibbs states. Okay. And I think it's interesting because interesting things happen from the point of view of complexity theory when you look at different regions of temperature, right? So let's consider the general problem of producing Gibbs states on a quantum computer, and look at what happens when you interpolate from the regime of preparing exact ground states to preparing maximally mixed states. No? So what we've seen from the result that I told you earlier, and also some others that appeared at a similar time, is that a quantum computer is good at producing high temperature Gibbs states, no? Because they're the simplest ones in a way, no? Because they're close to the maximally mixed state essentially. No? So preparing these Gibbs states, if you define this problem a bit more carefully that I'm doing here, belongs to the class of BQP, no? Because a quantum computer can do it efficiently. Okay. So now you can think of what happens when you lower the temperature. Okay. So what happens is maybe interesting, because what we know now, also from basically classical statistical physics, is that at some point, sampling from the Gibbs distribution is going to become NP hard. So there's a temperature that is some constant, and below this temperature, maybe related to phase transitions, it's not very clear whether it's related to phase transitions or not, the problem becomes NP hard, meaning that you don't expect either a quantum or a classical computer to do it efficiently. Right? So at some point, you go from a regime where it's easy for a classical or for a quantum computer, because part of this regime is also easy for classical computers, and then you have some sort of hardness phase transition into the low temperature regime where it becomes at least NP hard. And not only that, but if you go to even lower temperatures, in particular close to the ground state, where beta is poly n, then it's known from let's say big results in quantum complexity theory that this problem becomes QMA hard. And this QMA is essentially the quantum analog of NP. And there's some conjectures, open questions in quantum complexity that are about whether this QMA hardness somehow extends a bit more into a bigger range of temperatures, right? So it's not very clear how this NP hardness, the classical NP hardness and the QMA hard somehow interpolate, right? So there's some nice open questions here, about what is exactly the whole phase diagram of complexity, right? We know some points, but we don't have the whole picture. So I think this is this leads to some maybe interesting and I think very difficult questions. So far we kind of know the easy ones, like this one we were able to do. Okay, so now I want to talk about the last result, which is related, and it's really about the complexity of these Gibbs samplers and what kind of problems they can do. Okay, so now what we want to do is we want to have a model of quantum computation that uses these Gibbs samplings. And for this, we expect that we have to go to low temperatures because at high temperatures things are somehow very simple. For low temperatures, we expect complex things to happen. So maybe we can look for interesting particular cases where we can do nice computations, right? So the question is whether we can do quantum computations by thermalizing at low temperatures. Okay. So if we choose the Hamiltonian of the system adequately and the Gibbs sampler also adequately, as part of a family of the ones that I defined, whether we can solve interesting computational problems, in particular problems that a quantum computer will be able to solve. And this is related to some ideas that appeared before about basically doing models of quantum computation that have to do with open systems and with dissipation. I think these are maybe two of the famous papers in this area. So what we do is a bit like this, but with the Gibbs samplers, with these new Lindbladians, essentially. And this maybe to explain a bit more, what we do here is nice to maybe highlight something that is maybe a bit better known in the community. Hopefully some of you have heard of it, which is a model of quantum computation, which is one of the most popular ones, which is the adiabatic model of quantum computation. Right? In the adiabatic model of quantum computation, essentially what you want to do is you want to do the computation by doing an adiabatic evolution from a very simple state to the complicated state that encodes your quantum computation. No? And you do this by doing some change in your Hamiltonian, essentially. No? And in order for this adiabatic model to work, what you need to do is, what you need to end up doing is to prepare a state of low energy, of low temperature, which will be like a ground state of a Hamiltonian that you want to prepare. No? And the fact that you can do this is essentially guaranteed by the adiabatic theorem of quantum mechanics. No? If you do this, if you go from one Hamiltonian to the other slowly enough, then you will converge nicely. No? Not only this, but we also know that this adiabatic evolution, just by standard considerations, like by trotterizing the unitary evolution and so on, you can implement it in a quantum computer efficiently. And not only that, but there was this very nice paper by Harnov and other people, which was the one kind of showing that this model of adiabatic quantum computation is interesting from the quantum computational point of view. And the reason why it's interesting is because it can reproduce arbitrary quantum computations. So if you can do something with a quantum computer in a circuit model, you can do it with the adiabatic model. And the way they show this is by showing that with this adiabatic computation, you can prepare this thing called the Feynman history states, Feynman-Kitaev history states. I will talk a bit more about this in a second. And also, you know that to prepare these states, there's some sort of efficiency guarantee that comes from having a gap. So if you have a gap, you know that you can go to the ground state efficiently. So now we have a different model, which has to do with having access to these Lindbladians that prepare Gibbs states, not adiabatic evolution, but Gibbs states, so thermalization with some bath. And the question is whether we can have a similar, analog to all these things, no? And in the paper that I showed earlier of Chen et al., they show that in fact, since these generators converge to a state of very low temperature, no, you have this, and they also show that this Lindbladian is implementable in a quantum computer, right? So essentially, what we did in this paper that I mentioned earlier is to fill these other two holes that we have here. Yeah. Good. So really, the result here is is the following. No? We define a class of problems, which is the class of problems that you can define for Gibbs samplers, and it is convenient for us in order to have the computational power that we want to allow for temperatures that are polynomial in n. But the Lindbladians, we were able to simulate the Lindbladians with a cost that was linear in n, in beta. Sorry. So the cost of simulating these Lindbladians is still going to be polynomial for a quantum computer, right? And then, so in a runtime, this polynomial system size of these Gibbs samplers, and you have to allow for measurements for some technical reasons. Maybe I don't have time to explain this. What we show is that essentially the class of problems you can solve with these Gibbs samplers is equal to BQP. So it's equal to the hardest thing that quantum computers can do. So if you have access to these Gibbs samplers under these conditions, then you can reproduce arbitrary quantum computations. In order to show this, we go through this history state construction that I mentioned earlier. No? Essentially, what this is a Hamiltonian that is very special, and it's really, I think it was Kitaev who came up with these things, and this was really a revolution for quantum complexity. This is essentially Hamiltonians that are local, and they're constructed in such a way that their ground state encodes a quantum computation. So you have a ground state, which is the ground state of this Hamiltonian, and the ground state takes this form. So you have the gates of your circuit, which will be these unitaries, and then you have a clock, and somehow the clock tells you at what point in the circuit you are. So what this means is that if you have access to this state, if you're able to produce samples of this state, then you have access to the full quantum computation. So you can basically reproduce it, reproduce the full quantum computation. So being able to obtain these states is as hard. Well, it's not as hard. It allows you to reproduce quantum computations. No? So then our task is to see if we can reproduce these states with our Lindbladians. No? And if we're able to do this, then we have a dissipative model of quantum computation, right? And yeah, this is essentially what we show. That if you're able to, you can descend these Lindbladians in such a way that you converge to a Gibbs state, and for low enough temperatures, since the Gibbs state is close to the ground state of your Hamiltonian, then essentially you convert to something that looks a lot like a history state that we wanted, right? And in order to prove this BQP hardness, what we need to show is that our Lindbladian converges rapidly for a thermal state that has enough overlap. No? So we have to take beta to be large enough, but also not too large. No? So there was because if we take it too large, then we're clearly allowing for too much power. No? So we were able to just take it to be a polynomial in system size, essentially. So it's very small temperatures, but still allows you to get a non-trivial result. No? So essentially is that. No? You have to show that this state that you converge rapidly to it, and then it has overlap with the ground state. No? So you need these two things that are somehow a bit in tension. And yeah, with this, essentially we show what I said, no? That if you have access to these Lindbladians and some measurements, and the measurements essentially allow you to guarantee that you have this ground state, then you have access to arbitrary quantum computations, right? So you have a model of quantum computation that has to do with this open system dynamics, no? So this gives some hardness guarantees to the general process of preparing gift states, no? with these Lindbladians. What this means in the diagram that I showed here, I'm almost finishing, is that there are some particular cases of Hamiltonians that are here in this chart where the complexity is the same as BQP, no? So it's basically the same as usual quantum computations, no? But here I'm talking about the specific Hamiltonians only, no? The ones that are able to reproduce quantum computations. Okay, so with this, I want to just start with a bit summarizing a bit of progress that has happened lately, no? And with this business of gift states of quantum computers and quantum experiments and so on, it's a bit of an active topic, and there's been nice progress. In particular, some progress in quantum algorithms for gift states, like the progress that I just showed, and so many other works that are appearing basically by the day, no? And not only that, but there's also been nice progress in another related problem, which is Hamiltonian learning, which has to do with once you have a gift state in your quantum computer, how do you know that it corresponds to the right Hamiltonian, no? And for this, there's been some super nice theory progress, and the problem is pretty much solved at this point. And there's also been nice experiments in particular, this one that I really like in ion traps by the group of Innsbruck, where they're able to actually learn a Hamiltonian after a thermalization process. It's more a closed thermalization process, but okay. But there's of course a lot of opportunities along these lines, no, of dissipative simulation of gift states and so on. No? In particular, I like to think that these algorithms that I showed earlier maybe have more like near-term or noise-robust implementations. It should be possible, but I mean, I'm sure people are looking at it. And in general, I think that this new progress in the form of algorithms and also these other things should allow you to maybe be able to probe and verify thermal quantum phenomena, so more statistical physics, maybe in regimes that are in the I don't want to say quantum advantage, but regimes that maybe are not so easy to explore by other methods. No? So it's a bit of an exciting time for quantum statistical physics. No? And yeah, with this, I just want to conclude by just highlighting the three results that I said. No? So a derivation of a microscopic description of microscopic master equation, efficiency at high temperatures, and also arbitrary quantum computations at low temperatures, and some of the open questions that I mentioned. I don't want to get more into that. And yeah, with this, I finish. So thanks a lot. Yeah.
Thanks, Alvaro, for a very nice talk that covered many topics. We have some time for questions or comments from the audience. Some students maybe can. Please.
So concerning this result 3, so can you then say something that, okay, if somebody runs adiabatic computing on D-wave at some temperature, then they cannot get any quantum advantage because the temperature is too high or something like this, I mean, when they go to the larger complex problems. So can you say something using your results?
Right.
To disprove someone's claim regarding quantum advantage, just arguing, okay, no, you are doing adiabatic, temperature is too high for this problem to be really have some speed up.
I don't think it will go along this line. I mean, basically what we're saying is that if you have a lot of power, I mean, if you're able to design these dissipative evolutions, then you have access to arbitrary computations. But I mean, I don't think this says anything about the adiabatic specifically. I mean, I guess one thing is if you were able to show that at high enough temperatures you have somehow, classical simulation algorithms, then this will disprove D-wave, no? But
so it's not related.
It's not. No, it doesn't go in that direction. I think. Yeah. I don't know if Yeah. Also, this D-wave thing is always like it's a particular family of like Ising Hamiltonians and so on. No? So I guess you'll have to look at these instances specifically. No, it's not general Hamiltonians. No.
Yeah, but I thought that your result may be so general that you can somehow.
Yeah. I mean, in a way, I don't think we say anything that the paper of Aharonov wouldn't say for the adiabatic evolution. No? In the paper of Aharonov says that if you can adiabatically prepare ground states, then you can do quantum computations. But I mean, this is not what D-Wave is doing. No, the D-Wave machines are more specific, I think. So it's a motivation for them, I think, this result, but it's not quite what they're getting. You know? So as a theorist, this is how I see it, at least. Yeah.
If I can comment, just if one takes your perspective, I thought that may be like argument like in favor of like algorithmic third law, that it takes many operations, it should take many algorithmic operations to cool down the system, right? Just, okay, but it's all conjecture and complexity theory. So other questions to Alvaro? Okay, other usual suspect?
Yeah, so just, I didn't know about this hardness plot. So is there, also for the students, could I, because it's the one, okay, you had it already, that somehow it's surprising that for very low temperatures, so beta to infinity, you have QMA hard. So is it really the purity that makes things not NP hard? Could you get like an intuition why something, it gets easier, no? Am I understanding this correct? I mean, NP hard is the hardest you can get, so QMA hard is easier.
QMA hard is harder than NP.
It's harder.
It's harder, yeah, because it's the quantum version of NP.
Okay. Then
so if you can solve QMA hard, you can solve NP. Yes.
Okay, but then QMA hard. Okay, so is there anything relation to purity? No, that's my question.
Right.
That's.
I think that's maybe. I mean, this has to do with. I mean, this is, I would say that's a bit of an open question, because what we know is that from these history state constructions, that somehow measuring the energy of ground states is basically the is the hardest problem that quantum computers can check, not that they can solve. It's the hardest because that's what QMA hard is. It's the kind of problems that quantum computers can efficiently check. So if you have a witness for the solution, you can check whether that's the right solution. Like in the same sense that NP is the class of problems that classical computers can check efficiently. So that we know, and that does have to do with the purity. I guess what people would like to know is whether if you allow for more mixed states, whether you can show something similar. And I think this is related to this transition to whether this QMA hardness holds for larger temperatures, and this is completely open actually.
Okay.
Yeah.
Thank you.
It's like one of the bigger open questions in quantum complexity.
Then
actually.
it's good I
Yeah.
asked. Because, thank you.
Yeah, sorry, maybe I should have spent more time here.
Other questions or comments? Okay, can I ask one question about those error bounds for your derivation of master equation? So this relaxation time of the, like, how is, because your derivation works in the regime when the time is much smaller than the relaxation time of the bath, and like how long would it take to thermalize actually the system? Like in realistic scenario, do we expect like this to take much longer than?
That's I mean that's a balance that you have to be careful with. No? So for instance, in a few slides after, what I told you is that for the system to thermalize in one norm, it takes logarithmic time. So if you put it in here, you don't get something very good, no? Because it grows with n. Okay. So it's not clear to me that this is good for guaranteeing that you converge to. So I don't think with this scaling you can converge to Gibbs states in one norm, but maybe you can converge to something that locally looks like Gibbs.
I see.
So that's maybe what happens in practice, no? And that in nature you don't necessarily go to the Gibbs state in one norm, but you go to something that locally looks like the Gibbs state. No? And this is maybe what this will allow you for, no? Because presumably local sorrows thermalize much more rapidly than global ones, no? So, and this is something that maybe is compatible with this scaling, yes.
And do you think that this upper bound is like artifact of the proof, or it's fundamental that it should
I mean, I don't know if you can improve it much more. So for instance, the improvement that we have over Mosgunov and so on is that they had some exponential in T over T bath. So we went from exponential to linear.
Okay, so
I mean, I don't know how much more you can improve it actually. I mean, okay, I'd like to think it's fundamental, but who knows? I mean, maybe someone else comes up with a better proof.
Okay, if there are no more questions or comments, let's thank Alvaro again.
Thanks.